Welcome, everybody. We're going to be holding our session on pathways in physics. This was a topic that many of you shared in our feedback survey that you were eager to hear more about. And we have an excellent speaker joining us today, Dr. Dean Lee, an RSI alum. So before we get started in our presentation, we are going to go over some of the basics of CEE for you all, especially for these new names that I'm seeing. So CEE, or the Center for Excellence in Education, was founded in 1983 by Joanne DeGennaro and the late Admiral H.D. Rickover, who was the father of the nuclear navy and civilian uses of nuclear power. The mission at CEE is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics, or STEM, and to encourage international collaboration between and among leaders in the global community. At CEE, we have four programs, one of which is the Research Science Institute, or RSI. RSI is a highly competitive 6-week summer science and engineering program open to rising high school seniors. Juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Next, we have the USA Biolympiad, or USABO. It is the premier U.S. biology education and testing program for high school students. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Biolympiad team has medaled at the IBO. Next, we have the Teacher Enrichment Program, or TEP. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. Finally, we have STEM Lyceums, which is us right now, a virtual club for high school students to meet once a month to learn about STEM career pathways from leading field experts. Industry professionals share cutting-edge research and offer unique learning experiences like scholarships and internship opportunities for high achievers. In the chat, you'll see a link to learn more about our programs if you would like to visit the CEE website at www.cee.org. Now we'll introduce our speakers. So Dr. Lee, Dean Lee received his PhD in 1998 from Harvard University. From 1998 to 2001, he was a postdoctoral researcher at the University of Massachusetts Amherst. In 2001, he joined the physics faculty at North Carolina State University. He became an associate professor in 2007 and a full professor in 2012. In 2017, he relocated to the Facility for Rare Isotope Beams and Michigan State University. His research includes studies of the nuclear many-body problem using lattice simulations, as well as machine learning and quantum computing algorithms.
Thank you very much, Rebecca and Shannon. It's my pleasure to be here. I think everybody can see the slide now. So I'll go ahead and get started. Okay, so this is Pathways in Physics. I'll tell you a bit about my pathway. So I'm Dean Lee, currently professor of physics at the Facility for Rare Isotope Beams. I'm also the head of the nuclear science department here. And we're located at Michigan State University. I should mention what exactly the Facility for Rare Isotope Beams is. It's what's called a national user facility run by the Department of Energy and Michigan State University. It's exploring isotopes. So I'll explain what an isotope is. In an atom, if we look inside, at the center of any atom is a nucleus. And the nucleus contains protons, which have positive charges, and neutrons, which have zero charge. And so this nucleus is what attracts the electrons around on the outside. And so in nuclear physics, we study these nuclei and the properties of protons and neutrons, which have this strong force in between these particles. And so an isotope is when you take a particular element, like, for example, carbon. Carbon has 6 protons. And if you add some neutrons to it, you can, for example, have carbon-12, which has 6 protons, 6 neutrons. That's a total of 12 total protons and neutrons. And that's the most common form of carbon. It's called carbon-12. If you add a few more neutrons, you can get carbon-13, carbon-14, and then you can get unstable forms of carbon, which is exactly what the Facility for Rare Isotope Beams is exploring. These rare exotic isotope. So let me go start from the beginning of my career. Actually, the beginning of my life is more like it. So I was born in California, in Redwood City, when my dad was doing his PhD. My mom and dad were living in Palo Alto at Stanford. And so I was born a long time ago, 1971. And I stayed there for about 1.5 years before my dad got a employment in Michigan, in the Upper Peninsula of Michigan, in Houghton, Michigan, in fact, and Michigan Technological University. And so in 1973, that's where we lived. So if you know anything about the Upper Peninsula of Michigan, it's a very snowy place. And so I grew up with my brother. So this is me. And my brother's there. We're, I guess, cutting a Christmas tree. And this is our puppy at the time, Taiki. It's my dad, my mom. So it was a small town where we grew up. It was quite nice though. And so here's a family portrait with my older brother Dan. By the way, my brother Dan, he did also majored in physics. After he got his PhD, though, in physics, he went into artificial intelligence. So he's a professor at Cornell Tech, which is located in Manhattan, where he does machine learning theory and robotics and AI. So when I was young, I played a lot of sports, did a lot of music. So here you can see my brother and I were playing ice hockey. That was quite common at the time where we lived. We also played played the violin and did some piano, so a lot of music as well. And so here you can see our family a little bit later. While I was in high school, you can see our dog Taki there. And so in high school, I went to the Research Science Institute in 1987, which is one of the CEE programs. And you can see me here. So that was my junior year in high school. At the time, the RSI, or Research Science Institute, was located at George Mason University, but now these days it's located at MIT. When I was at the Research Science Institute, my project, if I remember back, was on optics. It was a particular type of optics where they wanted to know how much flux of light was being scattered by a given aperture. It was an interesting project that I did that summer. And then I also, as part of the CEE with the RSI program, I also did the Weizmann Institute program in Israel, where I spent a few weeks at the Weizmann Institute in Israel, where I learned a lot of quantum physics, some group theory. So that was actually instrumental in terms of getting me interested in physics, that Weizmann Institute program. So then in 1988, I went to Harvard University. So my brother, who was a year and a half older than me, also went to Harvard and majored in physics. And so for me, that sort of made it kind of easy to decide what I wanted to do. I know a lot of people want to know how I decided that I wanted to do physics, how I chose these things, because you're probably also thinking the same thing yourself at this point. So when I was in high school, junior high school, actually elementary school, junior high school, I had a lot of interest in mathematics, and was interested in abstract problems that one could solve with mathematics. And while I was in high school, I started to learn that physics is a place where you could apply a lot of this beautiful mathematics to do problems that nature somehow has picked up and found quite important for the behavior of our universe. And so I found this quite fascinating. And so I went to Harvard University to study physics. So I actually stayed at Harvard for my undergraduate and for my PhD as well. And my PhD advisor was Howard Georgi, who's a very well-known professor at Harvard, who is now retired, but he was great. You can see him here. He almost looks like Santa Claus. So at Harvard, I was interested in doing what you'd call the unification of forces. So there is the gravity, which is a very weak force. There's something called the electromagnetic interaction. So this is something you're probably already familiar with. If you have charged particles, like two electrons, they repel each other. This is the Coulomb interaction. And these are mediated by the exchange of particles called photons. This is what's called the electromagnetic interaction. There is another type of interaction that's called the weak interaction, which is responsible for the decay of, for example, the neutron. The neutron will spontaneously decay into a proton, an electron, and something else called an anti-electron neutrino. But then there's also this very important force called the strong interactions, which is what holds the quarks inside of a proton or inside of a neutron, and also binds the protons and neutrons together in nuclei. And this is essential for what we study here at the Facility for Rare Isotope Beams, the strong nuclear force. But the idea was that there's some unification of the forces. So there was already something called the standard model of particle physics, where there was a unification of the electromagnetic and the weak interactions, meaning that there was one description of both forces that if you just were to sort of point an arrow in a given direction and break a certain symmetry. In other words, you can imagine having an arrow that can point in all possible directions, but if you cool down sort of this arrow, it needs to find some location and rest at some particular point, and that breaks a symmetry because it's chosen a particular direction. A similar thing happens, which is called spontaneous symmetry breaking, that sort of breaks apart the electromagnetic interaction and the weak interactions that makes them quite different from each other. And so but at higher energies, if you're at hotter at earlier universe, sort of earlier times in the universe, the formation of the universe, you would see these two interactions as being quite comparable to each other. So the idea was that perhaps in the early universe, there was also unification of the strong nuclear force and the weak and the electromagnetic interactions, and perhaps even a unification of gravity with all of these other forces. So this is what's called grand unification theory, or the theory of everything if you also include gravity. So I was interested in perhaps doing this model building to try to understand how this all worked. Now, while I was doing my PhD, though, I realized that I was a little bit one piece of advice I like to give young people when they're trying to choose their career path is, number one, figure out what makes you happy, what really makes you happy. Find out the set of things that makes you happy. And then also figure out the set of things that you're good at. It will take some time before you figure out what you're bad at, what you're kind of okay at, and then figure out what you're good at. And I was starting to realize the things that made me happy and the things that I was good at. And I came to the realization that this idea of trying to do granular unification of the forces required a lot of high risk sort of guessing of what you think would be the future of the field. And I was naturally kind of risk averse. I didn't want the thing I told myself was that if I was to spend 20, 25 years of my life doing something that's perhaps very risky, I wanted that to be my own idea rather than following somebody else's idea. And so that's why I started changing my path. So I actually started shifting my direction away from sort of these very speculative theories of grand unification. And I wanted to do something where I knew there was more of an experimental validation of these theories. Basically, I didn't want to spend many, many years of my life doing things and then finding out later that they were not directly connected to physics. They were still mathematically consistent and interesting, but I wanted to have that connection to physics. And I wanted to be sure about that relatively in the near future rather than in the far future. So when I did my PhD, I ended up shifting towards understanding the strong nuclear force to understanding how quantum systems behaved, in particular systems where there were strong interactions and therefore lots of complications. And so my thesis was on exactly this, on sort of what's called strongly interacting systems in quantum field theories and quantum chromodynamics. So after I did my PhD, I then did a postdoctoral research, had a postdoctoral research position at the University of Massachusetts at Amherst. And that was a really wonderful time for me from 1998 to 2001, where I worked in the high energy and nuclear theory group at UMass, University of Massachusetts Amherst, where I worked with Eugene Golowich, Barry Holstein, and John Donahue. And I worked with several of their graduate students. And what I was doing was I was trying to develop new methods for solving strongly coupled quantum systems across many different fields of physics, in fact. The idea I had, and so this comes to a little bit of my strategy. So I'm trying to give you a sense of how I planned out my career. I had this idea that instead of trying to solve a particular problem in a particular field, I wanted to develop new methods for solving problems, brand new algorithms, new methods that were more powerful, more applicable to problems than what existed. And the idea was that if I had a better method of solving problems, I didn't have to specialize to one particular problem. I could use that for a bunch of different problems. And so that's what I was doing at UMass Amherst. I was really developing new methods for solving strongly coupled quantum systems in condensed matter physics, sort of materials type physics, as well as particle physics, sort of these elementary particle systems, as well as nuclear systems all together. And then in 2001, I took a junior faculty position in physics at North Carolina State University, where I was hired as a nuclear theorist doing low energy nuclear systems, sort of the types of systems I mentioned, like atomic nuclei, how the protons or neutrons interact with each other. Now, I should mention, so one of the things that I was working on was this idea of doing nuclear lattice simulations. One of the things I was really interested in doing was to understand these systems using lattice simulations. So here is a neutron, which is, as I mentioned, a particle that's a part of a nucleus that has no charge, no electric charge, and the protons, which have positive charge. And we had some attractive interactions between the neutrons and the protons, as well as between protons and between neutrons. And we want to try to understand how they come together, form a quantum system, and form all sorts of exotic properties. For example, these systems can form a superfluid, which I'll talk about a little bit later. And what I was doing was, as a faculty member, was developing ways of doing these calculations using Monte Carlo simulations. So Monte Carlo simulations are when you use random numbers to do calculations. So for example, if you want to estimate the area of a circle, one very simple way to do it is to put the circle inside of a square such that the circle is tangent or touching the square. And you know the area of a square, that's just the side squared, gives you the area, and you throw random dots in that square, and you find out the percentage of dots that lie also inside the circle, and that will give you a ratio of the area of the circle to the area of the square. So this is the idea of Monte Carlo simulations, and what I was doing was developing Monte Carlo simulations that would allow us to simulate these strongly coupled quantum systems like we see in atomic nuclei. So while I was at North Carolina State University, I met I met her online first of all, but then I met her obviously in person. I met my wife, Youngkin Cho, so she's a professional pianist. You can see here she's performing a concerto. I actually don't remember which concerto this is just from the picture, but she's a pianist. And we got married then in 2013. So this is actually from our wedding in Korea. We're wearing traditional Korean dress here in this picture. And you can see the foods out in front. It's part of the traditional wedding. Now I should mention my wife was a professor in piano at University of Texas Arlington. And so then we were trying to figure out a way for us to live together. She was in Texas. I was at North Carolina State University, so that was quite a long distance. And so we did a search to find a place where there was good nuclear physics and there was good music, in particular piano. And so the optimization problem ended up finding a pretty unique solution that it would be Michigan State University, where they were building this facility for rare isotope beams. So we moved to Michigan State University in 2017. So I got a position then at the facility for rare isotope beams, and my wife got a position at the Department the piano department in the College of Music at Michigan State University. So my wife brought with her three dogs. So this is Campu, the miniature poodle. This is Bella, who's so Bella's actually considerably larger than the other two dogs, but she's sort of in the background here. So she looks about the same size. So Bella's sort of a slightly oversized beagle. And this is Taiki, who's some sort of a mix, like a Chihuahua type mix. So Taiki, yeah, you may have noticed, has the same name as my old dog. So we named her after my old dog. And Winston is a dog that we got more recently, about 3 years ago. And this girl here is so the dogs are my wife's. This girl here is Sophie, who was a beautiful cat of mine. So I'm actually very sad because she passed away from kidney disease last month, but she lived to the age of 19 and a half years. So she was with me for 18 years. So she's very dear to my heart. So yes, we live with all these animals in a house. And this is my research group from a few years ago. There is a bunch of my students and postdoc, and there are significant others. This is my wife here. We're all going out to dinner to eat. And so I'll be talking about some of the work that these students and postdocs are doing. But I also want to mention that I've worked with several RSI students, and I know Max and Matthew are in the audience. I saw their names just a few moments ago. So I work with Kenneth Choi from RSI 2020. So this was great. So RSI for a couple of years during the pandemic was done virtually, and so they asked for alumni of RSI if they wanted to be virtual mentors, and I signed up, and that was really great. So I worked with Kenneth Choi, and then I worked with Max B. Lindgren. By the way, all these students have done quantum computing applications, quantum computing algorithms with me. Yeah, Max was RSI 2021. And then Matthew Petkowski was RSI 2023. I didn't do the RSI project with him. This was already back in person, but I connected with Matthew after he completed RSI, and we've done some quantum computing projects as well. So one of the things I want to mention, so this was a project that initiated with Kenneth, and we published a paper on it, something called the rodeo algorithm. So this is a project to use quantum computers to prepare quantum states. So what is it we want to do? We have a system of particles, and the challenge is that it's a fairly complicated system with many particles, and we want to be able to prepare the lowest energy state of the system, or maybe some low-lying energy state of the system. This is naturally what happens when you cool down a quantum system. It goes into its ground state, and you want to then interrogate it to find out, like, what does it look like if I hit it a certain way, or if I measure a certain property of the system. And so the rodeo algorithm is one way to do this with a quantum computer. So a quantum computer is when you use, instead of using classical bits, ones and zeros, quantum computer uses qubits, where we have a superposition of zeros and ones. This is what quantum mechanics gives you. And the whole idea of the rodeo algorithm is to use this quantum interference to make states that have the energy you don't want die away. So you start off with some random state that's a linear combination of the ground state and a bunch of excited states. And then you do quantum interference to make the excited states that have the wrong energy just decay away with each iteration. And so that's what the rodeo algorithm do. It's a bit like you have a bunch of different states on top of this bucking bronco, and only the state with the correct energy is able to survive after doing many iterations of this. So this rodeo algorithm, it has led to many projects that I mentioned Kenneth has done. Max is now working with me, and Zhengrong, one of my graduate students, to do a multi-state rodeo algorithm where we can prepare not just one state, but two states at the same time, and measure then the transition between these two states. from some operator. And Matthew is working on optimizing the Rhodey algorithm and also making the Rhodey algorithm work for large systems where it doesn't get, the performance doesn't degrade as quickly with system size, so that we can get a decent signal even for a large system. So what you do with the Rhodey algorithm is you have this tunable energy parameter, and you just do this quantum interference, right? And if there so happens to be an energy state at a given value of E, then you see an increase in the what we call the success probability. So we sweep through and we see sort of little blip at a given energy, and that tells us that we have a particular energy eigenstate. Now, if we wanted to then prepare a given energy eigenstate, we would sit on this energy here, and then we would just redo the Rhodey algorithm, and we would then purify the state so that it then is essentially as close to 100% just this energy state as much as possible. Another project that I do with my graduate students and postdocs is something that we call parametric matrix models. So we have an archive preprint. So if you're familiar with archive, this is the archive number, where we've developed a new machine learning tool. It's actually a completely new way of doing machine learning that doesn't use neural networks at all. So neural networks you can think of as artificial intelligence based upon the biology of neurons. Parametric matrix models is a scheme where we do AI, artificial intelligence, based upon the matrix algebra of quantum physics. So everything is a matrix. Everything is in terms of quantum physics. So if you know some quantum mechanics, you know that you're doing lots of things with matrices and linear algebra and getting things that are called eigenvectors and such. So the idea of parametric matrix model is to reduce everything sort of in the language of quantum physics, sort of like a quantum computer. Okay, and so one of the things that happens is that it turns out that scientific computing can be done very, very nicely using these what are called parametric matrix models. So here I'm showing you some results using these parametric matrix models where we've taken a bunch of two-dimensional functions. So these have various descriptive names that sort of tell you what they look like. Trigonometric, for example, has some sines and cosines that are wiggling in two different directions. We have something that looks like a clover leaf, something that looks like a cliff, a steep cliff here. And what we're showing is that the performance, if we take a set of points for this two-dimensional function, and then trying to interpolate between all of these training points and how accurately the various different machine learning methods work. And so here you can see various different methods like neural networks and other techniques, and their performance is around here. This is the normalized, the absolute normalized mean absolute error. So the higher it is the higher up this is, the larger the error. The lower down it is, then is better. And you can see here that parametric matrix model is systematically better than the other methods. This is simply because the parametric matrix model turns out to include more mathematics, more of the mathematics you want in the system than what you get from other techniques, in particular like Gaussian processes, neural networks, various other techniques. And here's another application where it's actually being used to do a quantum computing calculation. When we do quantum simulation, that is when you time evolve a system with a quantum computer, we have to have a particular step size for the quantum evolution, sort of how much time elapses with each iteration. And we want that time step to go to 0, but that's very expensive for a quantum computer. And so we have data for positive and negative values of dt, and we want to try to extrapolate to dt goes to 0. And so what we see here is data collected for the various energy levels of a quantum system and the performance of various multi-layer perceptron neural networks and polynomial interpolation. So the multi-layer perceptron is the dotted lines, and the polynomial interpolation is the dashed dotted lines, and the parametric matrix model is the dashed lines, which is systematically better than the other methods. Once again, there are reasons, mathematical reasons, that it's performing better than the other methods. So then we also do lots of projects using these lattice simulations that I mentioned before. And one of the papers we published recently in Nature was some technique called wave function matching. So the whole idea of wave function matching is that we want to do a simulation, but let's suppose there's a set of systems or a set of Hamiltonians. The Hamiltonian is the energy operator for a system. And suppose we can do calculations with a simple energy operator, a simple Hamiltonian, easily computable Hamiltonian, but there is another Hamiltonian sitting out here that's too difficult for the technique we're using. So the idea of wave function matching is to do a transformation of the Hamiltonian in a way that preserves everything that's important, but makes it closer to the set of easily computable Hamiltonians. And essentially what you're doing is you're changing the physics at short distances. You're doing sort of like plastic surgery to the interactions at short distances while keeping everything else at long distances fixed. And I won't get into the technical details of this, but that's what wave function matching does. And that allows you to do calculations that are relevant for what I study here at the facility for rare isotope beams, where we do calculations of atomic nuclei with 2, 3, 4, 5, 6, up to here showing you 58 particles, and the predictions we make from the theoretical calculations in comparison with experiment for the radii, how the charge radii of these nuclei. So this is something we would like to try to understand. It seems like with this wave function matching technique, we're able to make these predictions. Another thing we do is we try to see nuclear structure, where all the particles are, and we have this technique that's called the pinhole algorithm, where we have this sort of brick wall that kills the quantum amplitude unless the particles go through these particular holes that we call pinholes. And so what we do is we do the Monte Carlo simulation to prepare the low energy states of the system. But we also do Monte Carlo updates of the positions of these pinholes. So these pinholes then allow the particles to go through the holes. And by updating these holes, we know exactly where these particles are. We get a classical distribution of the particles. And that allows us then to see where all the nucleons are for carbon-12. So carbon-12, I mentioned already, we have 6 protons, 6 neutrons. For the ground state of carbon-12, we have this sort of interesting equilateral triangle where we have 4 particles here, 4 particles there, 4 particles there. And then if we look at some of the excited states, we get another equilateral triangle, slightly different sort of, but similar equilateral triangle. But then we have other states that have this sort of bent arm or sort of an obtuse triangular configuration. So this particular state is actually a famous state that's called the Hoyle state. And you may not know this, but this state is actually really important for formation of carbon in our universe. If the state did not exist and did not have a particular energy level in a particular location, then the production of carbon in red giant stars would be orders of magnitude smaller than what they are. And we would not have enough carbon then to form life, essentially. There would not be abundance of carbon that's enough for life as we know it. So this Hoyle state is actually people are really interested in the sort of the connection of the Hoyle state to make the carbon in our universe and therefore intelligent life. We also then can make 3-dimensional maps of the nucleons in oxygen-16. So just like we have 3 clusters for carbon-12, for oxygen-16 we have 8 protons, 8 neutrons, and we have 4 clusters sort of in a tetrahedral shape for oxygen-16. And then for neon-20, we sort of have an oxygen-16 sort of tetrahedron sitting here, but then we have an extra 4 particles sticking on the end. Some other things we do is we calculate the properties of hot neutron matter. Sort of if we have an explosion, a star burns all of its fuel. So by the way, when a star shines, it's actually doing nuclear reaction. But at some point it runs out of fuel. If it's a large enough star, what happens is you have something that's called core collapse supernova, where the outer part of the star collapses down and bounces onto the hard, sort of the rigid core, and this then shocks the material. It bounces back, and there is then hopefully an explosion. But it turns out that you need these neutrinos that come out, these weakly interacting particles called neutrinos. that is required to accelerate the explosion, to actually make it explode rather than just peter out. And so we did some calculations of how the neutrinos would scatter off these neutrons. And one project that we're very excited about that we're working on right now is on superfluidity. So we have a paper that's in progress right now where we think we have discovered a new type of superfluidity where there's not just sort of two particles are pairing together, but we actually have four particles pairing together, and the two particles can have different spins at the same time. So I should mention what exactly is superfluidity for those of you who have not heard of that before. So a superfluid is a material where, with a little bit of a push, the material can just flow essentially without resistance. And the reason this happens is you have quantum particles that are essentially doing exactly the same thing, and they don't scatter off each other as a result. So there's no sort of resistance to flow. They're all moving in the same way. But there is superfluidity associated with particles that are called bosons. Bosons are these sort of social particles where meaning that they can occupy the same state. But then there are also fermions, which are antisocial, if you have two identical fermions, they cannot occupy the same state. But it turns out with fermions, if you have an attractive interaction between two fermions, they can pair up together to form something called a Cooper pair. And this Cooper pair behaves like a composite boson. And so then now again, they can behave like a boson and form a superfluid. So this is the type of research we're doing to understand how this pairing up of fermions, or this what we call a quartet of fermions, is forming then this superfluid. So that is, in a nutshell, sort of my pathway in physics and some of the physics that I'm doing. I should mention my pathway was a little bit unconventional in that I started off doing grand unification and high energy particle physics, but then I ended up in low energy nuclear physics, which is quite a bit different. And so I had to learn a lot of things sort of as I was shifting my career trajectory. But as I was doing this, I realized I was learning a lot about myself in terms of what I felt I was good at, what I was happy doing, and this sort of guided me in my trajectory. So I'd like to thank you everybody for listening, and I'd be happy to then answer some questions.
Thank you, Dr. Lee. That was an awesome presentation. We love walking through how you started your journey to where you are now. That was incredible. So we're gonna go ahead and start in on our Q&A section. So first, let's see. What would you say was the single most impactful achievement in your academic journey? One that helped pave the way for milestones like studying at Harvard?
To be honest with you, in terms of choosing to study physics at Harvard, that a lot was the Weizmann Institute program, probably, where I learned some quantum physics and some group theory, actually representation theory, which was relevant for particle physics. I should mention at the time, though, so for those of you who are not familiar with the Weizmann Institute program, when it was operating back then, which was quite a long time ago, it might be quite a bit different now, but in 1988 is when I went. This is where you would go and you would sleep in these outdoor huts, which is quite interesting for a few weeks. But the actual experience I was a little bit unlucky in that when this was the first time I was traveling internationally without my parents or anybody else. And I actually had money stolen from me from my suitcase as I arrived in Israel. So it was a very it was a very hard experience for me personally, in that I was surviving there without any money. I was borrowing a lot of things. And then the director of the program was very kind. He heard that I had lost all my money. So then he gave me some money, and so that helped a lot. But then we took a tour of the old city of Jerusalem, and I think my pocket was picked, and I lost my wallet. So then I actually lost my money again. And so at this point, I was too embarrassed to tell anybody that. So I survived the rest of the program without any money and just surviving off the food that we're providing at the program. So it was very difficult for me personally, but the physics I learned there was awesome. Yeah, it is an experience in many ways.
Awesome. And have you ever considered pursuing a career in economics or maybe even something outside of academia? If so, what factors influenced your decision to choose a different path?
Yeah, so the thing is I really enjoy trying to understand what nature is doing. That for me, I mentioned try to find out what really makes you happy and what you're really good at. And I realize that what really makes me happy is to try to understand something that I think is universal. That is something that was really appealing to me is that it was fundamental. It was something. Think of it this way. Suppose you know there's other intelligent life in the universe. Okay, and they probably have different biology. They have lots of different, maybe they have different economic systems, definitely for sure. But the physics that they study will be the same. And I really like this idea that our civilization is studying something that would be universal to the rest of the universe. And this was very appealing to me. That is the importance of that was profound for me.
Awesome. So let's see. Andy here is asking, I was wondering, since you study subatomic particles and isotopes, do you use colliders in your research? Specifically, maybe the new laser Wakefield accelerators.
Yeah, so the laser Wakefield accelerators are a new sort of technology to try to go beyond the accelerators that are being used today, which is very promising, but sort of future technology. At the Facility for Rare Isotope Beams, we accelerate these nuclei to about half the speed of light. And so we have this typically a heavier particle beam, or it could be a lighter nucleus as well, and it hits a target and it smashes everything, and we collect all the fragments that come out. So my experimental friends, colleagues do these experiments, and I work with them hand in hand to make predictions of what they'll see. So I haven't myself done the experiments, but I'm involved in the planning and the description of what they think they'll see.
And to follow up on that, since these rare isotope beams allow us to peer into atomic structure, are they all similar to accelerators?
The accelerator technology is, if somebody does accelerators for the Facility for Isotope Beams, they probably have some idea of how to do accelerators for example, for the Large Hadron Collider or another accelerator facility. So a lot of the same technology is used. Basically, the idea is you use electric fields to push a charged particle. You push it and then you pull it. You push and pull it to accelerate. For example, in a linear accelerator, there is also cyclotrons, which makes things spin around, where you have a magnetic field involved. But for linear accelerators, that's sort of the general principle.
And going back into your presentation, on the model you provided about nuclear latitude simulations, the distance between neutrons and protons were given as pi or pi. Could you explain that?
Okay, yeah. I should explain this diagram a little bit more. Yeah. So this is not supposed to measure distance. This is actually telling you that there is a particle being exchanged between the two. So there's a way of thinking about all the forces of nature can be thought of as the exchange of particles. Just like, for example, if I have two electrons that repel each other because they're negatively charged, there's a photon that's being exchanged between the two of them. And here, the particle that's being exchanged is what's called a pion. And that's why I use this pi symbol. I should have explained what that pi was doing there.
No worries, we have many students that haven't yet even taken their high school physics class yet, so they're building
Yeah.
on that knowledge here. All right, let's see. So, within your work of physics, are there any overlaps of different kinds of science that interact with your specific field?
Oh, yeah, there is many things that overlap. So, for example, there's lots of things in mathematics. For example, for linear algebra is all over the work that I do. A lot of linear algebra. I do some work in machine learning. So there's lots of sort of optimization, sort of applied math, computer science aspects of it, and now, when we do these simulations, these lattice simulations, we do things on the largest, most powerful supercomputers in the world. In particular, for example, we've been running on Frontier. Well, actually, now it's number 2, but it was number 1 for about the last 3 or 4 years at Oak Ridge National Laboratory. And so we work with computer scientists to optimize code so that we can do lots of parallel supercomputing operations at the same time.
And to build onto that, Caroline's asked, did biological science ever intersect with your field of study?
I really love animals. I adore all of my pets. If I wasn't doing physics, I would probably want to be a veterinarian. That's probably something I would have wanted to go into. But you only can you only can do one life at a time. And so this is the one I chose.
There's an alternate universe where you're a great biologist instead of a
Yeah,
physicist.
yeah.
Could you go more in depth into your research on the carbon atom? More specifically, how did you all discover the amount of carbon in the universe is perfect for life?
We didn't discover that, but I can tell you specifically, I can shed more details on the story. So let's go to the story of this Hoyle state that I mentioned. So Fred Hoyle is a British nuclear theorist back in the 1950s, yeah, 1950s, and there was a puzzle as to how much carbon was being produced in stars. So they were just starting to understand the nuclear reactions inside of stars. And they realized that it was very difficult to make carbon. The reasons why it was very difficult is maybe a little bit technical, but I'll try to explain it. Let me try to explain it. The problem is that the stars are sort of hot from the point of view of everyday life, but from the point of view of nuclear physics, the stars are relatively cold. And so you can't go from like four particles, four protons and neutrons to 12 particles and neutrons. You can't just jump from 4 to 12. You have to add sort of particles, one at a time gradually. And so the question is, so there's a very stable configuration, which is called helium-4. We have 2 protons, 2 neutrons that has a lot of binding. So there's no problem to get a helium-4 in a star. And there's no problem to get 2 of these guys. So the problem is that these 2 helium-4s do not stick together. They're actually not bound. And so they don't hold together long enough. And so the question is, how can you then produce carbon-12, which has 12 particles, if you can't even make the 8? Okay. And so it turns out that this state of carbon-12, called the Hoyle state, sits at an energy that is just perfect to make the reaction enhanced. The thing is, its energy level is very close to the energy level of 3 helium-4 nuclei. And because of that, it's enhancing the reaction rate. Now, Hoyle realized, so at the time, though, this state had not been seen experimentally. So Hoyle made a prediction, a very brave prediction for a theorist, that there must exist such a state because carbon is abundant in our universe. And without this state, it would not be abundant. And so he made the prediction, then experimentalists went out and actually found the state, and it was exactly where he said it was. Now, what we did was we've done calculations. So our group was involved in the first ab initio, or ab initio means first principles calculation, starting from scratch sort of calculations of the state. So what we are known for is showing the structure of the state, what it looks like, and what these other states look like, which was a topic of quite a bit of speculation and controversy.
And just looping back quickly to Caroline's question previously on biological studies, she's clarifying, have you crossed paths in the field of biophysics?
You mean cross paths with people, or cross what?
It says, to clarify, I was asking if Dr. Lee has crossed paths many times with biophysics.
Whether I have done any biophysics. I have not really. Partly because the type of physics I've been involved in is very sort of quantum-ish, quantum-ish, whereas a lot of the biophysics involves other branches of physics, like electromagnetic, chemical physics, stuff like that. And so I haven't done so much biophysics, but there is a lot of interesting biophysics that I read about, but I don't do the research myself on. In particular, I'm very interested in neuroscience and things related to lots of different things.
Awesome. So, Sophia's asking, what do you think are the biggest inhibitors to the implementation and the advancement of quantum computing? In a more broad context, what are the big issues and questions in physics that interest you the most?
In terms of quantum computing, we will need to get our error rates down when we do. So we have these qubits, and one of the things we need to do to have a quantum computer is to make these qubits talk to each other so that we have some what's called a two-qubit gate where they're coupled together. Now, the problem is that we need the error rate to be at the 0.01% level or less. If we get to that point, then there are techniques that are called error corrections that could be used to improve the quantum computing. And so we're actually not that far away from getting to this point, but we just need to get a little bit further down the road on that. So things are moving along, but there's still some more to do. Now, what was the second part of that question?
In a broader context, what are the big issues and questions in physics that interest you the most?
Oh, that interests me the most. Well, so I mentioned that I started off in grand unification, high energy physics. So there's a question as to whether there is any unification of the forces. So even though I'm no longer in that field, I'm very interested in that question because it hasn't been solved. What exactly? It turns out that a lot of the work in the last few years using the Large Hadron Collider to try to understand sort of fundamental particle interactions have been somewhat disappointing in the sense that a lot of the theories that were being speculated have been ruled out, so the mystery remains. And then related to that, there's a lot of questions about exactly what is dark matter. So this is connected with these elementary particles. The dark matter that we can't see them in typical particle physics experiments, but we know them indirectly from, for example, gravitational lensing effects when we look very far away in our universe. So the dark matter has gravitational interactions, but it's an open question whether they have any other interactions, and therefore we might be able to probe them in the future. Then there's also this whole question of dark energy in terms of the early universe, the cosmology, expansion of the universe. What exactly is causing this sort of dark energy that is something related to the vacuum energy, the vacuum energy density. There's been some recent developments that suggest that our idea of cosmology is not quite, the standard sort of picture of cosmology is not quite living up to what we expected. And so there might be some sort of time dependence to this sort of notion of dark energy. So these are really interesting questions that I think may be solved in the next maybe 10, 20 years.
So I'm going to change gears in our style of questions. We have a lot of questions from our high school students kind of around approaching research opportunities and transitioning from high school to post-secondary education. So Sophia's asked, what do you encourage high schoolers to do now in order to pursue your passions in research? Or do you have any tips for getting research experience with scientists like you if you don't attend a summer program like RSI?
It's good to connect with people locally. If there's somebody doing research, RSI obviously is great, but maybe there's somebody at a university or some place close to where you live where you can connect with people. Now, the challenge though is that is that a lot of these researchers are bombarded with these requests. So I know myself, I get so many requests to do research with me that it's a little difficult. But there are a lot of people doing interesting things out there. So my advice is try to read a little bit about what's going on out there. So it's not sort of you don't come as like a blank slate that you don't really know what you want to do, what you're interested in. Figure out sort of what are the things that are interesting, and then do a search to see if there's somebody close by that's doing something in that direction, and reach out to them. The worst thing that can happen is that they'll say they're too busy, that they don't have time to work with you. But be brave, contact them and see what happens.
And building on that idea of making connections, when you were a student in your undergrad, how did you build connections with both your professors and connections within, research teams, other students? Were there any tips that you have for our students about making connections and building relationships?
Yeah. So I remember when I was a freshman in college, I went around and just knocked on a bunch of professors' doors to see if they wanted to me to do research with them over the summer. And that's how I got connected with my future PhD advisor, actually, because he was interested. So I started working with him when I was a freshman in college. In terms of tips for how to make connections, one thing I can say is if you're a young freshman or maybe you're in high school, you think of these professors as being like some famous person, untouchable. You should really realize that they are your average person. They're nice, they're friendly, they're approachable, but you have to somehow make a connection in terms of that you can do something that would be interesting for them. So you have to say, I'm interested in this particular thing that I think that you're doing, and is there anything I can do to help in this direction? So try to figure out from their point of view, like, why would they want to talk to you? Sort of try to do this reverse sort of role analysis. Like, why would they want to talk to me? And then try to figure out how you can make that
I
happen.
thought this was interesting. Talon's asking, what advice would you give yourself as a high schooler? So if you can go back to yourself as a high schooler, what advice or feedback would you give?
Yeah, the advice I would give is not to worry so much about things that are not so important. So I have to admit that one of the things I stressed about a lot was what people thought of me, or not making a mistake. And so one piece of advice I like to give, maybe to myself younger, but to all of you who are younger, who are listening, is you will be remembered for the best things that you do. In science, you do a lot of things. Some of the things will be completely wrong. Some of the things will be just stupid. Everybody is stupid. Don't spend all of your time worrying about not being stupid. Try to make your A game as good as possible, and just focus on when you're doing your best work, to make that the best possible, and not worry about whether people think you're being stupid.
I think that's a great piece of advice across all fields. Christian is asking, I remember that you mentioned switching what you specifically studied. Say I want to study something specific in physics, and then I change my mind later in college. Is it possible for me to switch to a different topic similar to what you did?
Yeah, absolutely. You can definitely switch. You just have to know why you're switching. You have to, my advice is, have a plan. Understand, if somebody were to ask you, why are you switching? You have to have sort of a good strategy. You have to know, one piece of advice I like to say is, go in the direction that you think is forward. That direction may change, but you have to have some reason why that is forward. It can't just be something else. It has to be, I have a plan, and this is the direction I'm going.
To add in on that, so, a lot of these students, when they're applying to college, they're looking at the different programs that they can apply to. Do you have any recommendations for how students can, look into specific programs or find a environment that works for them?
So are you talking about high school programs, or are you talking about college?
College.
Oh, yeah. So you mean picking a college in particular?
Yes.
Oh, okay. Yeah. So definitely you should go visit the campus, see what life is like there. So the college experience is very important, in that a lot of your closest friends will probably be your college classmates. So you will remember them for the rest of your life. So I can give you an example. My college roommate, you can look him up. His name's Carl Diceroth. I had an incredible roommate. He is one of the most brilliant neuroscientists in the world. If you look him up, he has award after award after award. But we've talked a lot about, like, what our futures would be, how our careers would go, and things like that. So it's really important to think about whether you will be happy there while you're in college. So think about the environment, but then also think about what field of study you really want to pursue. And whether there are people doing, if you're interested in research, whether there are people doing research in that area. And the other thing I want to mention is, if you're picking sort of a college, think in terms of what you want to do in terms of your career. So does that help you achieve what you think you want to do at this time. Of course, there's uncertainty and everything, but try to have a plan.
I think we got time for our last two questions. So, what advice would you give to someone who is starting their journey in quantum physics and mechanics?
Yeah, if they're starting their journey in quantum physics and mechanics, I would say there's a lot of things going on in quantum physics, quantum mechanics. Keep up with what's going on in quantum computing, but also keep up with what's going on sort of in other quantum fields. So not everything quantum is quantum computing. Most of my work is not with quantum computers, but actually studying quantum systems using classical methods. The quantum computing is sort of the future, but keep track of sort of the whole breadth of quantum physics. There's so many things. There's quantum sensing as well that is an emerging field. So my advice is to be broad in terms of learn a little bit about everything, but then try to figure out what you are most interested in and try to get deeper knowledge in those areas.
Awesome. So, last question for students that are looking to gain some practical experience, especially maybe like over the summer, are there any programs or readings that you would suggest that they do to kind of broaden their perspective on physics?
It depends on what field it is, of course, but there is, these days on the internet you can essentially learn anything. So I would just do a Google search or whatever search engine you prefer, and just watch a bunch of videos on, for example, on quantum computing. There's a ton of material by, for example, like IBM has a ton of material. And in fact, so Max and Matthew learned a lot of their stuff from reading some of this stuff. But in machine learning, there's probably even more material on machine learning and AI. So do lots of reading by yourself. So sometimes people think that they need to take a class to learn something, but it turns out you can learn things independently quite well as well.
Awesome. Thank you so much, Dr. Lee. Thank you for answering all those questions. And again, thank you to the audience. Those were incredible questions. I was so happy that you all participated, and we have a lot of thank yous in the Q&A for you, Dr. Lee, for your incredible answers. If anybody has any additional questions, they can email me at rebecca.carter@cee.org. I'd like to thank again our speaker, Dr. Lee, the audience, and our incredible sponsors for this programming, including the Claude Moore Charitable Foundation. Without them, we would not be able to keep this programming cost-free to all our students. So again, thank you to our sponsors. Thank you again, Dr. Lee, for joining us.